Welcome to this session on global impacts of local climate policies. We will be talking to John Sturman from MIT and Bent Erik Bakken from DNV GL. I am Jan Moberg, and the CEO and the publisher of the Norwegian Tech Voice, TU Media. And we are here at the Polytechnic Association with the MIT Club of Norway, and we have the pleasure of inviting you to this unique session. Climate change is a global phenomenon, but the policies tend to take regional and national scope. And they are primarily measured within national borders and appear to be expensive in that content. Now we will hear from Professor John Sturman, Director of MIT System Dynamics Group, a co-director of MIT Sustainability Initiative. John is a world authority on climate policy and how to impact them. John, you have advised US governments and many lawmakers. You're an author of standard textbooks on modeling complex systems, and has also initiated climate models and games used by tens of thousands globally. I know you have some interesting perspective to share with us on this topic. So, John, I'll leave the word to you.
Great. Well, thank you very much, Jan, and it's great to be with you and everybody, and also with Bent Erik, who got his doctorate in system dynamics in our group at MIT. So what I'd like to speak about today is the issue of speeding the transition to alternative vehicles as one very important aspect of the climate transition that has to occur in order to have any decent chance of limiting global warming to no more than 2 degrees C. So the focus for the issue today is how fast a transition to clean, zero or low carbon vehicles could cut the greenhouse gas emissions from transportation. And that entails how the world's light duty vehicle fleet could convert to alternatives such as battery electrics, BEVs, possibly also going along with autonomous or shared vehicles. To get that, I want to start out with a very short demonstration of our En-ROADS climate policy simulator. This model is freely available. I'm going to show you the website is right there, so you can check it out yourself. But let's just do a couple of quick demonstrations with it. So at the global level, on the left graph, we have total global primary energy consumption with historical data up through the most recent, and then the shared socioeconomic pathway scenario 2 as captured in our model. This is primary energy on the left, greenhouse gas emissions that result from that on the right, and down below, a wide range of policy levers. For right now, let's focus on the impact of electrifying the transportation fleet. When I pull this slider here, we're electrifying land-based transportation, not aviation, not shipping seaborne. So let's take a look. In the reference case, we're looking at 4.1 degrees C of warming, expected warming by the year 2100. Let's put a pretty heavy incentive in for electrifying the land-based vehicle fleet. And you can see it did nothing. It didn't change the global expected warming level at all. Why is that? Well, look on the left, you can see that the electric grid is dominated by fossil fuel, including a very heavy use of coal. This is a global model. The heavy use of coal is not so much in Europe or North America, but in China, in India, in Indonesia, and many of the emerging countries of the world, where auto fleets are growing very quickly. So as I pull that lever, you can see, if you look at the left, a small change. You can see that coal is increasing while oil is decreasing. That's the consequence of switching to electric vehicles. You've got to charge those batteries, and you're going to do it unless you have other complementary policies with more fossil fuel. So the coal wedge, also the natural gas wedge, and the renewables wedge, that's here and here, they grow a little bit, but if you're your batteries with dirty electrons, you're going to get a shift in where the pollution comes from, but the greenhouse gases don't change very much. So that's one problem. If I look at another policy, so here I've got coal being eliminated from the global energy system through a combination of taxes and regulation on coal and heavy subsidies for clean, green renewables, wind, solar, storage, et cetera, hydro. Now, that by itself lowers the expected warming to 3.4 C. And now if I electrify pretty intensely, you do start to see a benefit. But it's still very modest. And the reason for that is that the long lifetimes of vehicles constrain the rate at which you can turn over the fleet. So let's put a little context here, looking at the United States. In the United States, transportation is about 29% of total greenhouse gas emissions. And of that, light-duty vehicles, cars, SUVs, pickup trucks, the favored vehicles in the United States, are almost 60% of that. So that means that 17% of total U.S. greenhouse gas emissions are coming from cars and SUVs and pickup trucks. So how quickly can we transform the automobile system to be carbon-free, electric, possibly autonomous, and shared? A number of analysts out there, including Tony Seba, but he's far from the only one, have predicted that it's going to be a very fast transition, and it's going to happen largely without the need for government policy because of a dramatic drop in the cost of EVs, including a dramatic drop he's projecting in the cost of the batteries, allowing longer range at lower cost. In particular, he's forecast 95% of all U.S. VMT or VKT, vehicle kilometers traveled for you all, will be in self-driving electric shared vehicles in just 10 years by 2030. That is not possible, and let's take a look at why. So this is data for the United States showing the retirement of vehicles, cars and light trucks, cars in red, light trucks in blue, as a function of the age of the vehicle. And this is a recent set of data for just a couple of years ago, characterizing the U.S. fleet. And what you can see is that naturally new vehicles are hardly ever discarded, only really because they get into crashes, and that the discard rate goes up as they get older, and then it tails away. The average year or age of discard for cars and light trucks is around 16 years, with a long tail of even older vehicles that are still on the road and only get discarded, decommissioned, and recycled much later. So what we, our group, David Keith, my colleague, Sergey Naumov, and a student, Samantha Houston, what we did was we ran a simulation assuming the discard distribution you're seeing here, and we made the incredibly optimistic assumption that right now 100% of all new vehicles sold going forward are battery electric vehicles starting today. And then the question is, how long does it take before, say, 90% of all the cars on the road are the new technology, the electric cars? We've done research on what it is, and people's mental models are extremely poor. They dramatically underestimate how long it would take. It would take approximately 20 years, even if 100% of all new vehicle sales were battery electrics starting today, because of the long lifetime of those vehicles. And of course, that simulation is hugely optimistic because we're only selling 1% or 2% at most of vehicles in the United States that are electric or hybrid electric, even like the Prius. And that's, of course, due to the fact that there's low awareness still of electrics. There's a variety of makes and models. They're still quite expensive. They have limited range compared to gasoline vehicles, and there's inadequate charging infrastructure. So if you're going to make a faster transition in order to reduce greenhouse gases from transportation fast enough to be consistent with the 2-degree pathway, you've got to have government policies to speed that shift. And the mental model, the usual way people think about it, is shown here. On the left, we have the fleet sales and discards of internal combustion fossil-powered vehicles, and on the right, the analogous structure for electric vehicles. And the theory is simple. We can provide tax incentives and direct subsidies for consumers. We could provide tax incentives and direct subsidies for automakers. We could give EVs access to HOV lanes. We could have subsidies, incentives, and even government-sponsored build-out programs for charging infrastructure. And if we do that, EV sales are going to go up, ICE sales are going to go down. And as that happens, as the fleet turns over, you'll see the share of the vehicle fleet on the road shifting from ICE to electric. That's the dominant mental model. And what I'm here to tell you is that's not the way it works. When people buy an electric car, they already, in the United States, a very mature auto market, 250, 260 million vehicles on the road, they're trading in an existing vehicle. Okay, so that's not so bad. Now we modify the model. It says when we sell a car, either ICE or EV, somebody's going to be trading in an existing car. So what happens? It means we have this relationship here. Every time somebody buys an EV, they're trading in an ICE vehicle until much later, at which point some people will be trading in their old EV for a newer EV. But we'll ignore that for right now. So what happens? Well, the mental model still works fine. It says, okay, we stimulate EV sales, and that leads people to trade in their existing ICE vehicle, which leaves the fleet of ICE vehicles, emissions start to go down. But that's not true. Ask yourself, where do those cars that are traded in go? Real question. And the answer is they go into the used car market. So let's put that structure into the picture. When you trade in an existing vehicle, ICE fossil-powered vehicle, it goes into the inventory of used ICE vehicles available for purchase. And eventually somebody's going to buy that car and put it back on the road, put it back in service. So what's going to happen here? Well, EV sales go up from your very expensive incentives. Trade-ins of ICE vehicles go up. The inventory of used ICE vehicles will balloon. And the more effective the subsidies, the faster it's going to grow. And that inventory will grow until prices for those used vehicles fall enough that somebody's going to buy them. That person who buys that used vehicle, maybe a late model SUV that gets 15 miles per gallon, I'll let you translate into liters per kilometer, but a very inefficient vehicle, costs a lot to run it, but it's going to be so cheap to buy that people are going to say it's worth it. And what that's going to do is it's going to suppress EV sales. And so what you end up with is a policy that stimulates used ICE sales, which go back onto the road. And you've created a balancing or negative feedback loop here that I call the wasted subsidy feedback, because you've paid a lot of money to try to buy EVs. The consequence is, to the extent that it works, they're trading in their ICE vehicles. That simply piles up used cars until they become so cheap that somebody's going to buy them and put them back in service for their full life. And you can see right here, eventually, out of this total ICE fleet, those vehicles are discarded along the lines of that distribution that I showed you a little while ago. So what needs to be done here? What needs to be done is you need additional policies that speed up the discards out of the ICE fleet. And that policy is cash for clunkers, or C for C. We did this in the United States during the financial crisis, not to help with the climate, but to stimulate the auto industry, which was in a serious downturn. And in fact, General Motors and some others required federal bailouts. But the purpose is to keep the used car inventory from piling up so high that it then suppresses sales of new electric vehicles. So a cash for clunkers, C for C policy would look like a payment to the consumer as a subsidy for buying the EV, but you only qualify for it if you turn in an existing ICE vehicle which is sufficiently inefficient, on a trade when you buy that EV. And when you turn it in under the C4C program, the vehicle is decommissioned, discarded, shredded, and all the materials are recycled. And there's ways to do that. We did it in 2009. So we know that it's verifiable. So how would that work? Well, now you've stimulated vehicles. A lot of ICE vehicles are traded in, but at the same time, you're directly taking them off the road. So the inventory of used ICE vehicles doesn't go up, might even fall. Used ICE vehicles won't fall in price, might rise, and you stimulate EV sales. If you don't do this, then not only do you have to wait a very, very long time to get your fleet transitioned because of the long life of vehicles, but it's counterproductive. The subsidies that are costing the government a lot of money here end up subsidizing people to buy used ICE vehicles. So this is a policy that's under active consideration by certain members of the U.S. House and Senate. I can't comment on that, but let me show you a simulation of our model showing what might happen. So the red line, the reference case, where electric vehicle share of the installed base, that's what you see on the left, does grow slowly, but it only gets up to a little over 20% by 2050. If you add on top of that the Cash for Clunkers program, you get a much higher share by 2050, and there's uncertainty around that, of course. And the emissions, the greenhouse gas emissions in the graph on the right, associated with those vehicles fall dramatically, much faster than they would under the reference case. So the fundamental lesson here is it's necessary to empty the bathtub of the existing fleet of ICE vehicles on the road. But there's two ways to empty the tub. One way is to pour less into the tub, and that's the current theory. Get people to buy electric vehicles instead of ICE vehicles. And a lot of people, experts, sincere, smart people, believe that's all you have to do. But it's not enough. You also have to open the drain and get those vehicles permanently off the road. You can't sell them as used vehicles. You export them to other countries. You've got to get them off the road if you want to transition the fleet in time. This requires active, coordinated policy. Let me stop there and thank you all, and I'll turn it back over to you, Jan and Bent Erik.
Thank you, John. There's so many questions when I hear this talk of yours, and we'll get back to that. This is very interesting. I'll let Bent Erik continue. Bent Erik Bakken, the Deputy Director of DNV-GL, Energy Transition Research, also a professor at Oslo Met. DNV-GL and you, Bent Erik, you've just done some research showing that Norway has again punched above its weight, in the sense that we've had some policies going on that's also not only helped within our borders, but also helped
emissions from vehicles. So that's one thing we have looked at, and that is exactly the same story you're telling, John. Secondly, we did actually do 2 years ago a study for China in terms of accelerating their energy transition, and there we, as you indicate, John, we looked into having much more electric vehicles inserted into their system. But we did that, as you indicate, at the same time as we decreased the use of coal in electricity. So that's what I show here. So that, you know, this concerted policy program led to a lot less emissions than the base case. So instead of cutting the Chinese emissions by about 50%, as was the base case, they are reduced by almost 2/3. But even then, and that is quite important, even then, for the next couple of years, or even the next 10 years, compared to our base case, there is actually more non-renewable electricity being used. There is more renewable electricity being used, but we have to remember that you know, increasing the use of electric vehicles will, in those nations where electricity is very low use of electricity, that, you know, that will increase the electricity demand so much that that also non-renewable electricity will increase. But as we see to the left here, the total emissions is still a net positive effect on that to reduce the emissions. So just very briefly, as you mentioned, John, Climate Interactive, your colleagues in DC, they foresee it for 1.1 degree Celsius warming to 2100. And you see, in particular in the northern part of the world, the heat increase has already been over 4 degrees Celsius. So what is causing this? Fossil fuel combustion is at the center of this, as I show here. There are other reasons also for this, but the global warming and climate change, you know, has a lot of effects on the environment and feeds back onto how the greenhouse gases are being put out into the to the environment. So that is, of course, why we want to increase the use of electric vehicles, and as you say, we need to do it the right way. Just to say a little bit about Norway here, we have a population of 5.5 million people. That's less than 1/10% of the world population, and we have about 0.5% of the world passenger vehicles. But over the last 10 years, more than 10% of global battery electric vehicles sold have been sold in Norway. But these vehicles are slightly larger than the average vehicles. Most of these vehicles have been sold in China, but the Norwegian ones with a very high Tesla share are larger. So in terms of the batteries being in these vehicles, 15% are actually in Norway. And so, you know, this is something we want to look at, and there's a lot of public debate in Norway onto whether this is too expensive. So we have looked into this, and we find that about the national effects of the Norwegian EV policy cost $250 for each ton of CO2 mitigated. Other people, so the government recently issued klima kur, so the cure for the climate, they find a slightly lower price of that carbon, but at about $200 or 1,500 Norwegian kroner. So it's very clear to us, so we have investigated that that if you want to have a sales share of 90% by 2025, or 100%, which is actually the policy goal, you need to extend the current policy. If we were to follow the EU average policy, which is quite strong still, we would not see that at all, and the 90% mark will be delayed by about 15 years. And if we remove the support entirely, you know, eventually by 2100 all cars will be electrified, but we will delay it a lot. So what we are saying then is that there is a need for a global perspective. This is very expensive, so there are cheaper ways of reducing emissions than putting them into electric vehicles. As you mentioned, John, about 1/3 of transport of global emissions are energy sector, are transport related. As I mentioned, battery costs are extremely important in terms of the cost of an electric vehicle. Typically 25 to 33% of that vehicle is the cost of the batteries. So we asked ourselves, you know, if we account for the global emission effect, what is the true cost of carbon for the Norwegian EV policy? And we are so lucky as to have a global model of the emissions, and you know, it is, we are quite proud of this, as noted in the New York Times last fall. And New York Times, they picked up on the fact that already in about 3 years, global oil use will peak, and as is stated at the bottom here, this has to do with the introduction of electric vehicles. So our model then, you know, is influenced by a lot of things, but as we show here on the top, policy enters on all aspects of life, so to speak, on the final energy demand, on the primary energy supply, and on the energy transformation into electricity in particular. So this model then consists of 10 different regions where we look into this, and some issues are regionally specific, but some things cross over the boundaries of regions, and battery prices is a typical example of that. So here we highlight only transport and the power supply sectors. So what we see is that government support, you know, impacts the sales of battery electric vehicles. That's all well and good, and there is no question about that, as you very clearly showed, John. But that has an impact on the battery price. Why? Because the fleet of vehicles, they need these batteries, and they generate battery production, and there is a learning curve. So for every doubling of installed capacity of batteries over the last 10 years, we've seen a 19% reduction in the cost of these batteries. And as these are a main component of the price of the vehicle, you know, it does influence the sales of these vehicles. But not only that, the lower the cost of the batteries also enable the batteries in the cars to be bigger. And that is a very good thing, because that increases the range and the utility of these vehicles. Then, also interestingly, that the transport sector and the electric vehicle sales and the fleet also work very closely with the power sector, because variable renewables also need batteries to function well. They need storage, and we already have the battery price in the power supply to provide that link between the power supply and the transport sectors. So, as you might guess, and as I've talked about already, when the sales of electric vehicles increase, so does electricity demand. And then, also very importantly for the electric vehicles, that strengthens the electricity system and the power grids in particular. And that is very important, because not all nations are like Norway, where there is ample electricity and where a total electrification of the car fleet would only increase electricity by 15 to 20%, whereas elsewhere in the world where electricity is not used as much as Norway, it's extremely important to strengthen the grid, especially in the poorer parts of the world. But indeed, this is exactly what is happening, and that increases the probability of having fast recharging stations. So you improve the fast recharging density, thus further making it more convenient to have an electric vehicle. So this is the basic understanding we have of the energy system. And then this leads our base case to show that by 2050 in the world, about 3/4 of the car fleet is electrified. But as you mentioned, you know, this is not really fast enough, but that's not my point here. My point is that this shift of the vehicle fleet to electricity, it is the most significant contributor for world total energy demand to peak by mid-30s. And as we see here, in spite of the fact that the number of vehicles, cars, are almost doubling to 2050, the energy use in transport sector, so that's not only cars, that's also ships and trains and aircraft, is actually flattening out and declining towards the end of the, or towards the mid-century. So then we asked ourselves, you know, what are the real consequences of this national policy of Norway that we think is a good one? What is the cost? And when we look into that, we used this simulation model. So we substituted the forecasted full base support of Norwegian EV policy in that model after 2000 with EU level support. So when we do that, we see that the global EV fleet will grow, but actually quite marginally, slower, of course, without a Norwegian policy. If there is no Norwegian policy, the battery prices globally will be higher, and the global fleet is reduced. So it would be 2% lower than with the Norwegian policy in place in 2030, and 1% in 2050. So that sounds, you know, very marginal. But if we look back into the emissions reductions caused by this, you know, it's not fantastic, but in terms of the effect of the Norwegian policy, it is actually 5 times more emissions reductions outside of Norway than inside of Norway. And if we go back then to well, here we see the fleet impact of no Norwegian EV policy. So in Europe, of course, the impact is very high for the first 10 years. The European fleet would have been a lot less, because up to 2018, I think it is, half of all electric vehicles sold in Europe were actually in Norway. But if you go back then to the implied carbon price of Norwegian EV policy, it's actually not the 200 I started with, but $50 per ton. So that is, you know, only twice the current carbon price, the ETS price in Europe. So as a conclusion, climate change is a global issue. When devising national climate policies, global effect actually are what matters, and global policy models are required. And such models need to include feedback between sectors, as I mentioned, because technologies such as battery costs, also crucial for uptake of variable renewable energy and electric vehicles, they are interrelated. So with that, I give the floor back to the moderator, please.
Thank you, Bent Erik. John, I have a couple of questions for you, but first I'd like if you have any comments to the presentation from Bent Erik.
Quite a few, but let me be very, very brief. So first of all, I fully agree with you, Bent Erik, that it's important to take a global perspective in modeling these issues, precisely because of the positive externalities that you identified. We're all focused on the negative externality of carbon emissions that harm the climate and everyone. But there are positive externalities of, for example, Norway's successful efforts to grow the electric vehicle fleet. The reduction in costs, the improvement in battery industry scale that drive global costs down, create a positive externality for the rest of the world. So it's really important that your model and our models as well account for those. And then, our model, your model and our model differ numerically in some of the details. That's actually expected and normal. But what's really important for everybody out there is they give the same policy recommendations. So we make a distinction between numerical sensitivity, which is obvious that different models do and should give different numerical values. But policy sensitivity is the most important thing, which is, do the different models agree on what should be done? And in this case, they clearly do. It's not going to happen fast enough unless there's active government policy, as Norway has demonstrated. And when you do that, you're able to get us closer to that 2-degree pathway. Alignment here, and I don't see any significant disagreement on the policy recommendations. A couple other really quick ones. Our models do include the battery learning curve and scale economies and other such endogenous mechanisms of technological progress that bring the costs of electric alternative vehicles down over time. I didn't show any of that for time, but they're present in the model. And that means that the policies that Norway has implemented so successfully that boost EV ownership actually make EVs cheaper and better with longer range, more charging infrastructure for everybody a little bit later and around the world. So that's very important and fully agree. You also mentioned briefly the importance of greening the grid. Norway's fortunate to have hydro in abundance. The rest of the world does not. So in the United States and most of the rest of the world, we've got to green the grid as fast as possible as a complementary policy to the rollout of alternative transportation. And there's an important synergy there that needs to be accounted for, which is that the large number of batteries in electric vehicles most of the time will be sitting idle. And that provides, at no marginal cost to the grid, given that you've purchased your electric vehicle, the storage capacity or most of the storage capacity you need to balance load and generation in a world of very high variable renewable generation. So that's a very, very important synergy or complementary attribute of these policies that's in your model, and it's in our model as well. Let me stop there and see what other questions Jan has for us.
Thank you, John. We already have a few of our viewers eager to put their hands on your sliding levers model. That's very fascinating. And just could you comment quickly on the sensitivity of development of battery price in that model?
Yeah, so in the En-ROADS model, it's an aggregated global model, so we do have the learning curve for storage, but we're not looking at batteries in cars separately from stationary battery storage, separate from other forms of storage. But in some of the submodels that we've built, including the one that I illustrated with the Cash for Clunkers program, we do look at battery costs, and they have been coming down. Bent cited a 19 or 20% learning curve, experience curve rate. That's right globally, and there's no reason to think in terms of the underlying chemistry and materials science, no reason I'm aware of to think that learning curve won't continue for some time. How fast we go down that learning curve depends on how fast the industry can build scale have reliable long-term contracts and certainty, more certainty about how quickly this industry is going to develop. So obviously the global pandemic has thrown a lot of uncertainty into that issue because people aren't driving, they're not buying cars. That will be temporary, but there's bigger headwinds here that matter quite a lot. For example, in the United States, where President Trump and the administration have been rolling back environmental regulations, have created a massive debate with legal action between the federal government and various states and the auto companies about weakening what we call our CAFE standards, the corporate average fuel economy standards that mandate that the efficiency of all vehicles rise at a certain average rate for each auto company. They're seeking to roll those back. Whether they win or not on that is unknown, but the mere fact that that's in flux and that there's uncertainty about that weakens the incentives that General Motors, Ford, Toyota, and other auto companies have to go fast enough into the transition to electrics. And it puts hundreds of billions of dollars of capital investment, product development that they've already committed to at risk. So that's a serious problem. Certainty here matters as much as what happens to battery costs next year.
Just a real quick comment on the pandemic. Isn't that also an opportunity for you to test the model that you have?
Absolutely. So, the most salient fact about the pandemic is, as a contrast to climate change, is right now, and we hope this will change quickly, but it's not expected to. Right now in the pandemic, there's no treatment, there's no cure, and there's no vaccine. For climate change, it's exactly the opposite. We have the technologies we need to cut global greenhouse gas emissions dramatically now. And those technologies are ready to go off the shelf, and they are safe and effective. And they are, first and foremost, energy efficiency for especially buildings, homes, commercial, residential, and industrial facilities. There's enormous opportunities for energy efficiency. Then it's the renewables, wind, solar, storage to go with them. In many parts of the world, including parts of the United States, wind and solar with storage are now cheaper to design, permit, build, and operate than simply operating existing coal-fired facilities. And there are similar technologies available right now today for afforestation, for deforestation reduction, for reducing methane and nitrous oxide and the fluorinated hydrocarbons that are the other principal greenhouse gases. So we have what we need right now. What we lack is the policies to get us there quickly, and that in turn is a function of insufficient public and business support for those actions. And underneath that is an erroneous mental model that it's impossible or very expensive to do without fossil energy. That's just not true anymore. We can do it, and that's the big difference between the pandemic and climate change.
Thank you, John. I have one final question for you before I have a question for both of you. I just wanted you to comment on the question that many people have. Isn't it good for the climate that we sort of use the cars already produced, even though they're fossil?
So this is a question about life cycle analysis and what's the energy payback time for a vehicle. And it's certainly true. There is, it does take energy, and that's largely fossil energy today, to produce a car. And that embodied energy and the embodied emissions matter. But it's a small fraction. The life cycle analyses on automobiles shows that the production of the car, including all the materials upstream in the supply chain, and the decommissioning and recycling of the materials after the car is taken off the road, are a small fraction of the emissions. The vast majority of the emissions associated with a fossil ICE vehicle come from burning gasoline to run it.
Okay, thank you. Then a question to both of you. Just a comment on fuel cell technology. Is that part of your models or is it a separate work?
So if I start, we look into fuel cell electric vehicles, and we find that these vehicles are not the solution for smaller vehicles. So light-duty vehicles, we do not see that they will take off at all, and that has to do with the energy equation. If you produce hydrogen, which is the basic fuel for them, if you take it from electricity, you basically have to reduce the efficiency of the electricity by a factor of 3 to 4. So both the cost will be the fuel cost will be 3 to 4 times higher, but also the whole energy system will be extremely inefficient. So we see fuel cell electric vehicles not to take off for where there is a good battery alternative. But when it comes to when there isn't one good alternative, so that is for heavy trucks, we clearly see that happening. If you want to decarbonize transportation, heavy transportation, you need fuel cell electric vehicles also. So we see that happening, but we don't see that taking off like for electric vehicles, already with us today. The fuel cell heavy trucks will take another 10 years before they start to grow significantly.
John?
So I fully agree. The hydrogen fuel cell vehicle offers the possibility of fueling faster than recharging your electrics, but their cost is enormous right now, on the order of $100,000 unsubsidized, compared to electric vehicles, which are much, much lower right now, and conventional vehicles, of course. And there's no fueling infrastructure. So Toyota and Kia both have pilot programs in the United States. When they rolled them out, it was, the number of fuel cell vehicles that they were leasing to adventurous customers was in the dozens at most, and there were 1 or 2 fueling points publicly available. It just isn't going to get any traction as long as battery electrics become more capable, and they're well on their way to doing that.
Okay, thank you so much. I'd like a final comment or some points from both of you. What are the most pressing 2 issues that we're faced with in this topic, getting to the EVs?
Yeah, I think we have alluded to them. I think for the next 5 years, it is critical that governments actually do what the Norwegian government has done. And I see the current EU standard for vehicles, so the emission standards, which I think are 95 grams per kilometer, they will force part of that will happen through electric vehicles, and there are sort of accounting rules that favors that also. I think that is very important, but that is already on its way, and that makes that, in our view, when you come to 2033, half of all global vehicles sold will be electric. At that time, the disadvantages in terms of range, of course, they will still, on average, have less range than an ICE, and recharging infrastructure will not be on par with petrol stations, but the costs will be lower. The operating costs of electric vehicles are typically a fraction, half, or even lower. So the economy of electric vehicles are so that the vehicle electrification will happen with the policies we actually see in front of us. And some of us will expect that there will be a new president in the US a year from now, and highly likely that president will push more for vehicle electrification also. So that's another thing. At least that's something that is likely to happen.
John?
Well, I'm not going to comment on our presidential election. Let me just say that it would be very good for climate policy, for environmental policy, for national security, and for a host of other issues if we had an administration that was basing its decisions on the intelligence and on the science and not on whatever it is they're doing right now. But I don't think that's guaranteed at all. I agree with the points that Bent Eric made here. Let me just add, in order to have any decent chance of limiting global warming to no more than 2, we as a world have to cut global greenhouse gas emissions by about half in just 10 years and then continue rapidly down to 0 or even net negative by mid-century. The only way that's going to happen is with coordinated and aggressive policy that we don't have here. Even if the Paris Agreement was fully implemented, it would only, in our model, get us down to about 3.3. And essentially, no nation on Earth is on track to meet its Paris commitments. So we need much more aggressive policy, and that's got to include a significant price on carbon, which I don't know if you're still able to see my screen, but it doesn't solve all problems, but it is, if I can joke a bit, it's the one policy to take with you to a desert island if you can only take one. It's not enough. We need many policies. We've waited so long to address this issue that we have to do everything. We have to price carbon. We have to subsidize renewables. We have to especially invest in energy efficiency and electrification, not only in transport, but in stationary applications, residential, commercial, industrial buildings, and industrial processes. We have to make changes in the way we run our energy system and our agricultural system, so methane and nitrous oxide and the fluorinated hydrocarbons, that those emissions go down. We're going to have to cut deforestation dramatically. There's no silver bullet for this problem, but there is silver buckshot. It is still technically possible for us to limit warming to no more than 2 if we get lucky about how resilient the climate is. But we have to do it right away, start right away, and we have to do it on multiple fronts. I invite people to check out that idea themselves in the En-ROADS model. It's free. It gives you immediate feedback, so you can explore and learn for yourself. Because although I'm delighted to be here today, the fact of the matter is that, well, let me put it this way. Research shows that showing people research doesn't work. What's important is that everybody out there go and learn for themselves by trying these models on their own and come to your own conclusions. So go to n-roads.org and make your own judgments by experimenting with the model.
Well, John, thank you certainly for spending the afternoon with us. John Sturman from your net energy producing home outside Boston.
Yep,
and we hope you have a great day further on. And to Bent Erik, thank you for joining us. And thank you to the audience that we've had this afternoon.
Thank you very much.